Hello everybody, my name is Ivan Kolutza and I lead the Computational Biophysics group at SIC Biomaguna in San Sebastian. Today I will talk about what modeling can teach us about protein evolution. Heteropolymers are chains of monomers of more than one type, and contrary to blockopolymers, they are characterized by a complex sequence pattern. Proteins are a special class of heteropolymer. They are made of about 20 different amino acids connected by the peptide bond. The latter is a particularly efficient bond for polymerization. Proteins are the nanomachine of life, and their sequence is encoded on the DNA via a codon converting 3 DNA bases into one specific amino acid. The translation process from DNA code to protein code takes place in the ribosome where the proteins are synthesized. All life on Earth is based on the same principle and uses the same 20 building blocks. Hence, proteins are completely recyclable within one organism or by different ones, making it the perfect sustainable material base. Copying such a feature into industrial polymers could trigger the green revolution in chemical industry. The sequence of the proteins control the structure and the function of the proteins themselves. Typically, residues on a proteins are classified according to the relevance on the particular property under study: stability, catalysis, protein-protein interactions, or allosteric. During the course of this talk, I will derive the three main properties that define designability and foldability in proteins. Then we will apply such properties to study how key properties arise from the selection of sequence, a process that in nature is performed during the course of evolution. In order to understand the connection between sequence and conformation, we will start with the early mean field theories derived in the late 80s that connect a conformation and a sequence of an heteropolymer to the final folded state. We start by assuming that for each given conformation, the energy distribution of the sequence are uncorrelated to each other. That is to say that the probability of having energy A and B on a protein is equal to the product of the probabilities of having the energy EA and the energy EA and the energy EB independently. Hence, the free energy of an heteropolymer is the free energy per sequence average over all possible conformation. Following the mean field approximation, we can make an harmonic expansion in temperature, and we obtain an expression that has a specific temperature at which the entropy becomes constant equal to 0. This region is where we observe what is called the freezing transition. That's why we refer to this specific temperature as the glass temperature. So the final free energy of the system above the glass temperature is has a parabolic distribution, while below the glass transition temperature it's made of discrete states, each one of them with 0 entropy. The key parameters that identify the mean field model of heteropolymer freezing transition are the average energy of the interaction matrix and the standard deviation of it, plus the total number of conformations of the system and the valence of the bonds. You can read this expression as basically the average interaction per bond multiplied by the total number of bonds that each element on average sees, minus the entropic contribution coming from all the conformation that the system can adopt. A key element of all this description, as we will see later, is the definition of this number of conformations. The mean field model allows us to define a design temperature, or the temperature at which the system will adopt a specific conformation with energy ED. Since the target conformation of the design sequence must be kinetically accessible, the equilibrium conformation at the folding temperature TF must have the same energy, must be the same as the energy of the state identified during the design at the design temperature. So we equalize the two. This equal condition, which translates mathematically to equalize the free energy expression that we derive for a temperature above the glass transition to this to the energy of the design state, leads to a final expression for the phase diagram of the entire heteropolymer freezing system that is defined by this equation of state here that connects the folding temperature, the glass temperature, and the design temperature. We can draw such a phase diagram where we see that there are regions that are that depend on whether the particular system was obtained with a temperature, design temperature that is above or below the glass transition temperature, and whether the system was refolded with a temperature above or below the glass transition temperature. So the sweet spot for heteropolymer design and folding is for temperatures well below the glass transition temperature, for design temperature well below the glass transition temperature, and for folding temperatures well above the glass transition temperature. Of course, if the temperature is too high, we cross this boundary region where we go from a folded state to an unfolded state. As you can see, lower the design temperature, higher is going to be the folding folding temperature, which means that lower design temperature create more thermally stable proteins. The procedure, hence, to design and folding a protein can be described in this simple diagram where we wrote the energy of the protein as a function of two main parameters. C represents the contact matrix that defines if two amino acids are interacting in space, and S represents the interaction matrix that tells how strong the amino acid, the type of amino acid at position I is with the interaction of the amino acid type at position J. So during design, what we do is we fix a target configuration and we optimize the design sequence to minimize the energy to a global minima where both the structure and the sequence are optimized into a specific target protein. During the folding, instead, we take the sequence generated during the design and we look for the configuration with the lowest energy in the target with the target sequence, and that should, if the design was successful, it should end up in the same point in the phase space. Now, it's important to say that lower the energy, higher will be the protein stability, as we mentioned before from the phase diagram. And also, the theory is independent of the particular model used to represent the protein, because there is no prescription on how this structural matrix is defined, or in the mean field approximation that I showed you before. By definition of the mean field, there is no information about the topology of the protein. With the correct representation of the backbone hydrogen bonds in proteins and an alphabet of 20 amino acid types, a simple coarse-grained model can be used to design and refold natural protein structures that are taken directly from the protein data bank. The sequence with low energy on the natural target structure listed here have their global conformation free energy at the extremely close to the target structures. To measure such distance, we projected the entire conformational space over the distance root mean square displacement that is a common measure of structural difference. Smaller the value of the distant root mean square displacement, closer you are to the target configuration. Larger number corresponds to higher distances and hence larger basins of configuration. What this plot shows is that the caterpillar design sequences refold back to the target structure with a high precision. Hence, the caterpillar model is a designable protein model, in particular that is capable of reproducing the conformational space of real proteins. Now, one question that arises from this result is, can we generalize the properties of the caterpillar to any other heteropolymer? So before going into the wider category of any heteropolymer, one interesting result that can be done with such a model is testing what is the minimum alphabet size that can be used to design a caterpillar protein. Interesting, the caterpillar model predicts that the protein structure can be designed with a minimal alphabet of just 4 letters, while with 6 we recover the full folding resolution of a 20 letter alphabet. This is in a good agreement with mutation experiment identified 5 letters as the minimum alphabet. So this result will come out important later, but is also interesting already in itself, because it shows how you can use a simple coarse grain model to test fundamental questions about protein evolution and hence effectively evolution of life. So in order to go back to the question that we were discussing before, what it was so special about the caterpillar model that is capable of reproducing such a fundamental properties of real protein, in other words, design the structures in nature, we have to look back a moment at what it was, what are the prediction of the mean field theory when we ask the question about designability, which is what are the conditions at which design is overall possible and there is at least a solution to the design problem. So the mean field theory helps us define such a condition by looking at the entropy of an heteropolymer with a target configuration, like this entropy here, which is basically nothing else than the derivative of the free energy of this particular configuration, where we average over all possible sequences that you can place on top of this protein. So if you express this sum now and you calculate the derivative, you find out that the entropy is nothing else than the logarithm of the total number of sequences that you can place there minus this quantity. Now this, of course, we have assumed, and this is thanks to the mean field theory, mean field model, that you can thread any sequence on top of any specific configuration. Now, if you accept this hypothesis, then you end up with this expression that is one of the strongest predictions of the mean field theory. It tells that the alphabet size must be larger than the number of configurations per monomer of your heteropolymer in order to have at least one solution at of the design problem. This is a very important condition because it was actually given for granted for many years, because the reference models we used were lattice models, where this condition is automatically verified when with very small protein alphabet. So it was not considered to be a major obstacle in proteins. However, it is actually a fundamental property of heteropolymers. So you can verify this condition either by increasing the alphabet size or by controlling the number of conformation. Now, the problem is that this number of conformations is actually undefined, as we mentioned before, unless you introduce a proper length scale in the system. So in order to understand what this e to the power omega means, we first have to introduce a length scale in the system. And the natural landscape that we introduced recently to measure exactly this quantity is the folding resolution. In other words, is the distance, the structural distance, the minimum structural distance that you consider by which you consider two structures to be different. So if you are below this folding resolution sigma, two structures are identical. If you are above, these two structures are different. The other important parameter that we recently introduced is the directional interaction, and we have been arguing that in the past years now that with directional interactions you can efficiently control the size of this conformational space and effectively bring it down to manageable values where you don't need very large alphabets. So how do we prove that? Well, what we have to do is to actually measure this quantity, this number of conformation in a system, and test whether indeed this relationship is valid first, and then use it for useful prediction. So we have done this recently, where we took a simple bit spring model, where now by introducing the length scale sigma that I mentioned before, the resolution, we could actually count the configuration, analytically count the configuration of a simple trimer with just 3 bits. Then with the computer simulation algorithm that is based on particle insertion, we could grow a chain starting from the trimer and compute the increase in the number of conformation in the system, or in other words, the entropy of the increasing polymer. Then, by adding the directional interaction as surface functionalization on the particle, we could compute exactly how the effect of these directional interactions on the number of states of the system, and hence measure how the directional interactions are key for the designability. So that led to our this final phase diagram, where the black line represents the line at which the alphabet size is just large enough to have a designable heteropolymer. Above the line, hence, we have the designable region phase. Below this black line, we have the orange region that is non-designable. So in other words, you cannot find a sequence that will fold univocally in your target configuration. And the system would just, if you lower the temperature, will just get trapped in a random glassy state. We then performed also direct design and refolding of these patchy heteropolymers with the different patches, and these are represented by the dots on the phase diagram. And where you see a round dot, that's where we could actually identify a sequence that folded back to the target structure. So from our direct simulation, this is a designable system, while the crosses represent a system where we could not identify such a sequence. And as you can see, the phase diagram and the simulation are almost a perfect match, except for the large patches, which are also, I have to say, are more challenging to simulate and to study. So maybe we don't know if this is a shortcoming of the model, or maybe the simulation itself was not accurate enough. So there is another very important result, is that in this phase diagram predicts that when you have a system with 2 directional interaction per monomers, the minimum alphabet size that you expect to have a designable system is about 4 letters, which is exactly, as you remember, what we obtained with the caterpillar model and that we showed before. So even proteins fit perfectly on this diagram. And interestingly, when we actually increase the conformational space that we looked for folding for two patches, we found out that if you wanted to increase this configurational space, you quickly reach the 20-letter alphabet that we have today. So it could be very well that the size of the alphabet that we have today is necessary to reach the wide conformational space that proteins need for a life function. Another interesting result of this phase diagram is that when you don't have any patches, so here there will be just the vertical axis, the line, the phase diagram line cross at an alphabet size of about 1,500 letters, and this is for a chain length of about 50 monomers. So what this result suggests is that indeed there is an alphabet size at which even without directional interaction you can design a system, and this is basically the Go model limit for who among you know are familiar with protein modeling, but it is far away from any practical application and from any sensible solution for nature application in evolution. But as soon as you increase the number of directional interaction down to 2, you immediately go to much more simpler phase diagrams and alphabet size and hence manageable systems. So hence system with no directional interaction can be classified as non-designable, which is a parameter we can use to discriminate between polymer system as designable or non-designable depending on their number of hydrogen bonds or other type of directional interaction. So we looked, for instance, for hydrogen bonds along the backbone, and as you can see, the typical polymers that are sort of industrially produced, among them most of them are non-designable, but there are some that potentially could be used for creating the backbone of an artificial protein. And we are working now to try to understand if we can exploit these properties to design artificial polymers to fold. So now a potential application of a designable heteropolymer would be, for instance, the engineer of single chain nanoparticles with controlled topology and surface patterning. The precision of the refolding is high enough that you could have potentially applications in the catalytic domain, where you could physically place active sites with a very high control on the space geometry and realize local catalytic activity if, of course, you push the particle size down to the nanoscale. We could also design these single chain nanoparticles to have very complex topologies and reach even very complex knots like the one listed here, which especially for the applications that are interesting to this community, it is a very interesting system to test and study how topology arises in proteins or heteropolymers in general. Another application that I want to mention that is related to this reverse engineering of evolution is to understand how functionality can be detected in proteins. And this is a recent development that we are still working on. So an application of coarse-grained protein design is the classification of the amino acid function. By comparing correlation patterns in artificial sequence and natural ones, we could classify as structural the residues that have strong correlation in the artificial set, while functional as the one that have a stronger correlations in the natural set alone. In this example, which is of the FKBP family, protein family, we could identify in green the functional residues, which are one-to-one matching with experimentally identified residues that are essentially for the binding pocket of this protein to its natural ligand. So this was done just by comparing the artificial set of sequences with the natural one without any biological information about the protein. So I think it's a very interesting way to study the evolution even of proteins, because if the set of sequences that are generated with the artificial protein design can be considered as an artificial representation of protein evolution. Again, in the same direction, another key feature of protein function, as we mentioned in the beginning, was protein-protein interaction. So protein design can be used to test the evolution of protein-protein interaction. For instance, by designing binding pockets of different size to bind specifically to a ligand protein, we discovered a rationale for the size range of the pockets that is normally found in nature. So pockets that are too small offer a binding affinity that is not strong enough to be of practical use, while the ones that are on the other hand of the scale have very strong binding affinity that is unnecessary in for nature application, because they could lead to irreversible binding, which is not something that normally you want in biological systems. And it's interesting that exactly this range is what we found fits perfectly with the naturally occurring binding site. In particular, the small ones, they really match very nice with the lower bounds that we found in our simulation. It is also interesting to point out that these pockets are all specific. So if you try to have other proteins binding to it, even with the same structure but different sequence, the binding affinity will drop very low. So again, the protein design can automatically give you binding specificity and evolution properties. So still in the direction of protein interaction, another important aspect of protein evolution is the optimization of protein-protein interaction to avoid aggregation. And aggregation is one of the major pitfalls in protein folding and can lead to a lot of unwanted disease and cell death. And the problem is that if protein aggregation occurs, normally is a very stable thermodynamic state that is very hard for the cells to get rid of. That's also one of the reasons for why they are usually quite toxic. So it's not surprising that cells that have such a very high concentration of proteins inside them have developed a regulation mechanism to avoid the expression of proteins at concentration that are very high, and that in such a concentration such expression level is lower for proteins that have higher propensity for aggregation. So that's a very reasonable experimental observation. What was striking about this experiment is this linear correlation among the expression level and the aggregation propensity, which indicates that proteins aggregation occurs in an uncorrelated fashion. In other words, as long as you keep the protein below its aggregation concentration, you will not observe cross aggregation or aggregation induced by the presence of the other proteins. Now, this is it seems to be a very general statement looking at this data, so we decided to put it to a test using again our protein model based on the heteropolymer design that we discussed until now. So we use this protein design tool as an artificial evolution testing ground, and we designed a simple protein model and we tested for cross-aggregation between different protein species that we artificially evolved, like we call it protein B, A0, and we designed about 7 different protein species that you can find in the paper. But the main result is a phase diagram like this, where we showed, in this case, this is a binary mixture where we have protein A in contact with protein B, and it's a phase diagram of different concentration of protein A and protein B. And the main result is that you can see that the folded region of each protein is quite orthogonal to the others, and it doesn't really depend very much on the concentration of the other protein, which means that as long as you are below the critical concentration of each protein, there is no effect of the other protein and there is no cross aggregation. This is a very important computational result that simplify enormously the hard game of evolution to add always new species of proteins to increase the complexity of function that cell needs, because it doesn't, as long as the proteins are kept below their aggregation concentration, the cell does not have to worry too much about the interactions with the other proteins in solution. And so we tested this experimentally, and we consider 2 proteins that are evolutionarily disconnected. So in other words, this means that these 2 proteins that we consider, namely the bovine serum albumin and the CT protein repeats 3, so this is a trimer of this CTP protein, these are evolutionarily disconnected proteins, so they have no common evolution history, and so their sequence, if there is any optimization of against cross aggregation, these 2 proteins couldn't possibly had such an optimization process during evolution to avoid their cross aggregation between each other. And as you can see, they also have quite different structures. So we first determine the aggregation of each protein separately, which for BSA, as you can see from this DLS data on the cluster size that they form, is about 4.55 milligrams per milliliter, while for the CTPR that has a very sharp and strong signal is about 1 milligram per milliliter. And this was particularly useful because such a sharp transition is a very nice signal for aggregation, if there is any. So for us that was perfect to test if there was any cross aggregation induced by the presence of the BSA. So we basically repeat the same experiment we did in the simulation, and we added increasing quantity of BSA to a concentration of the CTPR below the aggregation concentration of the CTPR, so below 1 milligram per milliliter. And increasing concentration of BSA did not change at all the distribution of the aggregation in the system up to concentration that were of 4 milligrams per milliliter, which were well above the CTPR aggregation limit. And of course, you have to be below the BSA aggregation limit of 5 milligrams per milliliter. But the total concentration of protein was above the one of aggregation of the CTPR, indicating that indeed as long as you are below, there is no aggregation. So with that, I would like to conclude just with a take-home message that simple models can be used to test fundamental evolution questions and have practical application towards the creation of new materials that are more sustainable and are modular based on a simple subset of building blocks, and basically that the simple models allow us to learn from nature how to build such materials. So I would like to conclude with by thanking the people that are working in my group or worked in the past, all the funding agency and all the collaboration that again I had the fortune to have in the past and that led to all the work that I showed you today, and thank you for your attention.